Hello, good evening. Welcome to module 4269, Green and Sustainable Chemistry. This is the lecture on kinetics and stoichiometry, and I see it very much as a perspective, or rather a change of perspective for you as chemists, and an introduction to the literature. I recommend to you Levenspiel and Vogler. Levenspiel is available on Google Docs, and Vogler is in the library, and I think there's also an e-copy there. This is where we're going to go this evening, and I'm going to go fairly quickly because, as I say, I'm assuming that you're going to, this lecture is just a starter or a helper for you to get into that literature. Okay. Again, you see this at the beginning of every lecture. It's just progress, and I don't want to talk any more about it. Okay, so what we're going to deal with in this lecture are single and multiple reactions, the degree of reaction, that's little x or Greek letter zeta, and the conversion, which is capital X. I'll talk about the difference between them in a moment. We'll talk about the reaction rate and the rate equation. We'll talk about overall yield and selectivity and instantaneous yield and selectivity. Okay. For the avoidance of doubt, let's just go through what I mean by some of these expressions. A singular reaction, a singular reaction. So A moles of A going to B with plus B moles of B going to C moles of C plus D moles of D. Or an equilibrium, where you have it going both ways. We can have multiple reactions, that is as parallel reactions. So A goes to D and A goes to U. So D is usually in these lectures desired, the desired product, and U is the undesired or a side product that you don't want. Consecutive reactions where A may goes to D, then goes to U, or A goes to U and goes to D, or parallel consecutive. And let's put that another way. I find pictorial representations often more useful. So we have parallel reactions. There you go. A going to D or A going to U. Consecutive reactions, there's one of the examples I just gave you, and parallel consecutive, which is a bit of a devil's brew or witch's brew, that there are many different forms. Why is this important? Because the form of the reaction will determine what, as a kineticist, you observe. That's why it's important. Okay, so moving on. First, let's think of the degree of reaction little x. I won't use the term zeta. I've put it in for completeness. Now, this is called many things. It's sometimes called the extent of reaction in some books. It's sometimes called the progress variable. But they're all the same. They're all little x. And the other variable is capital X, which is the conversion. Now, we need to define, and through this lecture we're going to define terms. The first one we're going to define is the stoichiometric coefficient. It is the number in front of each species in the equation, and it's symbolized by nu means the stoichiometric coefficient and I is the species. So for instance, if I is A, then nu is equal to -1 because A is disappearing, it's being consumed. If I is B, then nu is equal to +1 because I is being formed. And it maybe is obvious, but nu for any species I equals the differential of the number of molecules of I divided by x, that little x, the degree of reaction, and therefore that rearrangement is true too. I need to talk a bit more about x and little x and capital X, because one is an extensive variable and one is an intensive variable, but we'll get to that in a couple of moments. So let's talk a bit more about the degree of reaction, little x. It can be a real product, a molecule of which is produced each time the reaction event occurs, or a hypothetical product. It's an extensive quantity, so it describes the progress of the chemical reaction equal to a number of chemical transformations on a molecular scale as per the reaction equation. So the change in the extent of reaction, change in x, is given by dnB over the coefficient of B, if you're dealing with B as the product. And N here is the number of moles of B, and again, nu is the stoichiometric coefficient. Okay, this is basically just definition stuff, so I'm moving through it fairly quickly. Right, now we'll think about this concept in terms of single and multiple reactions. So for singular reactions, for a single reaction, the sum of the reaction coefficients for each of the species, so if I is equal to A in this case, will equal 0. So in this case, if I is equal to A, the coefficient is 1. If I is equal to B, the coefficient is -1. The sum of -1 and +1 is 0. And that is true for all singular reactions. So I equals 1 to S. S is the number of species, and in this case there are 2 species, so it would be I is equal to 1 to 2. Let's now take a multiple version of that. Let's do an equilibrium, so we have a forward and a backward reaction. And for multiple reactions, this time the sigma of the stoichiometric coefficients for species I to S and reactions J to R for reactions, again S for species, so it's going to be 2 species and 2 reactions, the ith component and the jth reaction. Let's take an example because they're always easier to do. Let's take the reaction of nitrogen and hydrogen to form ammonia, or the equilibrium rather. As a forward reaction, the stoichiometric coefficient of nitrogen is -1, it's disappearing. Of hydrogen is -3, it's disappearing. And of ammonia it's +2 because it's forming. The backward reaction, second reaction, is of course the same numbers with the opposite sign. So now, if you sum all of the new values for both reactions and all species, you have 0. Okay, let's continue moving forward. Now, again, degree of reaction for multiple reactions and definitions. N is the number of moles. It's an extensive variable. It depends on the amount of material in the system, irrespective of which one you measure. It can also stand for molecules as well. It's, as a chemist, I'm sure you're familiar with moving between those. N, same units as an intensive variable. Depends only on the component you measure. In this lecture course, mostly I'm using N in terms of molecules and little n in terms of moles, but it sort of is not desperately important whichever way around you do it. So the extent or degree of reaction, little x, is N. Let's say moles, as that's what the slide says. The number of moles of species I at time 0 minus N, the number of moles of species I at T equals T, divided by the stoichiometric coefficient of I. And it follows from these follow from that. Right, okay, let's now make sure we're happy about the difference, and let's define the difference between the conversion and the degree or extent of reaction, little x. So little x is extensive, depends on everything in the system, irrespective of what you measure. So it's talking about the progress of the entire reaction. Conversion is an intensive variable, and its validity is limited to what you measure. So in this case, capital XA, the conversion is the number of moles or molecules of A at time naught minus the moles and molecules of A at T equals T divided by the moles or molecules of species A at time naught. There is no stoichiometric factor in there. Therefore, it is an intensive variable. Of course, that will equal A extent of reaction divided by NaO. If we want the extent of reaction, the extensive variable, we need to divide our quantities by the stoichiometric coefficient for that species. Okay, so what I'd like to do now is just do a little exercise. We'll do an example first, where we actually are given the initial number of moles of the species. So this is a version of the water-gas reaction, which I think you'll recognise. And initially, we've got 4 moles of hydrogen, 2 of methane, 1 each of carbon monoxide and water. What I want us to do is develop expressions for the number of moles and the mole fractions as functions of x. Okay, well, we've got the initial numbers already, so the initial column is nice and easy. Initial row is nice and easy. Okay, the number of moles then of methane at some time x, the extent of reaction is going to be the initial number of moles minus x minus that extent of reaction, and likewise for each of the other components. And notice there you've got a stoichiometric coefficient of 3, so you clearly have to incorporate that into the relationship. The mole fraction, well, that's the number of moles divided by the total number of moles. So if we add all of these 4 numbers of moles up, you get a total of 8 plus 2x. So now all we do is for the mole fraction of methane, we want n, the number of moles, which in this case is 2 minus x, divided by the total number of moles, which is here. And this follows all the way through the table. Clearly, as the sums of the mole fractions is 1, therefore that must be 1. Okay, that didn't hurt too much, did it? No, I hear you screaming, it didn't. Good. Okay, so what I would like you to do now is I've put 2 equations up here. What I'd like you to do is to do the same thing again. This time, so you're looking for the number of moles and the mole fraction. So this time, your numbers of moles are given as 3 for methane, 3 for water and 2 for methane. Sorry, we'll start again, shall we? Your stoichiometric constants for reaction 1 will appear here. So that's as before, 1, 1, 3, 1. And for reaction 2, 1, 2, 4, 1. Of course, the methane and water will have minus signs in front of them, and the products on the right will have plus signs in front of them. So you've got your initial numbers of moles, so you can now calculate your numbers of moles along here. Now, in the extra slides, you'll find the field table. In this lecture, I can't move between them because, unfortunately, I'm on a laptop and I don't have a degree of control that I would usually have on a full-size machine. Good. I will just read you a couple of the answers so that you can see the working. So for number of moles for methane, you're looking at the initial concentration, initial number of moles. You've got to watch yourself as a chemist. You always use concentration, I do. But here we're dealing in terms of the number of moles. The initial number of moles, which is 2 for methane, minus x1, that is the extent of reaction 1, minus x2, which is the extent of reaction 2. And likewise, you can carry on here. The initial moles of water is 3. So that'd be 3 minus x1, the extent of reaction 1, minus, and this time we've got a coefficient of 2, minus 2x2. Anyway, same all along here. Now note for carbon monoxide, carbon dioxide and hydrogen, the initial number of moles is 0, so that's easy. And then you sum them, and then your mole fractions are your number of moles here divided by that sum, exactly as you did before. Good. Okay, so finally, this is really just to be sure that you know what you're doing in your head. Think about this for a moment, and we'll come back to it in a moment. But the kinetics we've talked about, or at least the stoichiometry we talked about, I'm now going to put into the context of the different reactors that you, different types of reactors that you may be working with, because actually it it determines actually how you do it. So the subject now is reactors, the context is reactors, but the subject is exactly what we've been dealing with here, kinetics and stoichiometry. So we're going to spend a couple of slides just looking at reactors and what the implications are of them. There are two types of reactors: batch reactors, and we mentioned these in the last lecture, and flow reactors. So here's a little picture of a batch reactor. You can control temperature. They're usually jacketed with a heated oil or to give you a temperature that you want. You can usually control the pressure, and you can usually control the mixing regime. The key character is all the materials are added to the pot and nothing is removed until the process ends. This is a liquid example. I've put this one up here, a semi-batch reactor. Don't be fooled, it is not a batch reactor. It's a type of flow reactor. All that's happened here is that you get the chance to do two reactions. Sorry, I'll re-say that. Be careful, it looks very much like another type of reactor, which is a flow reactor. But this one is a batch reactor because there's no way out. You're not flowing out, but you're doing one reaction to start with, and then you're adding another reagent to do a second reaction. So these reactions are drawn as liquid reactors. Equally, you can have solid batch reactors. And really, here's a couple of, they're called blenders, a couple of solid reactors, and effectively they have a giant mixing vein inside which goes round, and so you do the reaction on a solid basis rather than a liquid basis. Okay, now we come to the second type of reactor, which is a flow reactor. And the key word here is flow. So the most common type of reactor is what's called a plug-flow reactor. And it's normally fairly simple. You can control temperature, you control pressure, and you control the mixing regime. Effectively, you have feed going in one end. You may or may not have a packed bed in there. Again, this is the liquid version. And as you pump it down here, so the reaction occurs, and you get products out the other end. The other type of reactor is a mixed flow reactor. This is the one you mustn't get confused with a batch reactor. It's a flow reactor. You've got feed going in, it's being mixed, but you've got product coming out, and it's effectively the level in here is a steady state level. So it's just another type of flow reactor. Don't confuse it with batch. You can increase the complexity of the chemistry somewhat, and you can have multiple ones of these on a production line. But just information. Now, the other type of flow reactor is actually usually a gas reactor. Can be a liquid, but in this case it's a fluid bed reactor. The bed is a solid, usually catalyst particles or reactant particles, and the fluid is usually a gas. Can be a non-dense liquid, but again, this is the mainstay of the petroleum industry and some of the other stuff we're going to be looking at in this module. So you have flow going in and flow coming out. And as I say, we'll look at this in detail in a minute. There are implications for the process as to which of these types of reactor you have. Okay, let's now look at what some of those implications in terms of your thinking are. For a batch reactor, no implication at all. The number of moles or molecules of A will equal the number of moles or molecules of A at time 0 times 1 minus the, that's a capital X, so it's the conversion of species A. Fine, exactly the same form as we were using previously. But for flow reactors, we can't use that. We have to use, and what we're going to use is a molar flow rate. So if it's a batch reactor, yep, you can use N, but for a flow reactor, usually you will use fluxes F. And again, you have a diagram here, which I think helps to understand. And we will use moles per second as our flow unit in the rest of this lecture. Okay. I'll continue through the reactors in terms of the implications. So, hence, in terms of flow reactions, flow is there's a volume times a concentration in there, specifically. And again, F is always a molar flow rate in moles per second. So batch reactors, you're dealing with N. Flow reactors, exactly the same format. We're dealing with molar flow rates. I'm not going to click this now. This is a link to a lecture on some of the concepts we've been dealing with here, and I warmly recommend it to you. It's one of the Fogler lectures, and it's basically, it's not really a lecture, it's the web version of his book, and all the chapters are actually there. But if you concentrate just on the first 1 or 2 chapters, then I think that read with this lecture, I think that will help you quite a lot, or at least I hope it will help you. Okay, we need to think a little bit now, so that I know where I am. about the rate equation and the rate function. So let's have an equation, a chemical reaction. The stoichiometric coefficient is A of species A and B of species B going to R of species R and S of species S. Now, the rate of disappearance of A would be the statement of the rate of the reaction. Now, this is intensive. It's about species A. Now, because species A is disappearing, there is a minus sign there. Now, we would normally think of dNA over dt, which is fine. But we need to divide this by volume so that we actually, if that's the number of moles of A, we then have moles per cubic, moles per cubic meter per second. So we actually have a flux. As you're quite happily aware from your basic kinetics, minus RA divided by the stoichiometric coefficient will equal the disappearance of B, and so on and so forth. And this is the chemistry that you have been used to, I think, so that you think of the rate however you express it. Multiple is equal to a rate constant times the concentrations of the reactants raised to alpha and beta, where they are the orders of reaction with respect to those species. And that's how I think we would normally think of it. I want to be sure that you are happy about what the rate function is, and the relationship between the rate function. We can either do it in terms of mass, and mass here is W, weight, simply because if we use M, it's going to get confused with something else. So W is actually mass, or V is volume. So the relationship between either R-I, which is the mass or mass function, or Ri, which is the volume function, is actually like that. Okay, I'm just going to carry on. So let's now think about what rates of reactions are dependent on. They're obviously dependent on composition. That's what we've been looking at so far: concentration, pressure, and typically it's equal to rate constant times some function of concentrations. Now for us, for chemists, that's about the order of reaction, and I'll talk about that more in a moment. They're also dependent on temperature or light if it's a photochemical thing, and we think of the rate constant here as, here's just simply Arrhenius expression, pre-exponential factor A exponential minus the activation energy divided by RT, where R is the universal gas constant and T is the Kelvin temperature. Now, for reversible reactions, R is equal to the forward rate minus the reverse rate. For multiple reactions, again, this IJ should be subscripted. Rj is equal to the sum of Ri for 1 to Q and J for 1 to R. Like that. Really the same logic we had before, where J is the number of reactions and I is the number of species. Now, we need to think a little bit more about this, because I'm hoping what I'm doing is bedding this into what you already know from the first and second year. So here's if you like, putting all that together. that the rate is equal to some function of temperature dependent terms and concentration dependent terms, and as an example we might use something like this. So this is clearly some sort of Arrhenius term, and you've got concentrations raised to reaction orders and the like. And this is the form you would usually be interested in and be familiar with. The concentration of A raised to alpha, which is the reaction order with respect to A, and the concentration of B raised to beta, which is the order of reaction with respect to B, where the overall reaction order is beta plus alpha. Okay, I think the rest of this is reasonably straightforward. When you have a reversible reaction and equilibrium effectively, then the equilibrium constant, Kc, is the forward reaction divided by the reverse reaction, and that follows from there. Okay, we're in territory, I hope, of teaching your grandmother to suck eggs. That is stuff you've met before and is straightforward for you. Let's, however, think about the form of, for Arrhenius anyway, the form of the dependence on temperature. And what I'm interested in is the temperature rise required to double the rate of reaction. And this is your standard reaction coordinate diagram, and I won't worry too much more about that here. Okay, now there are two things I want you to notice here. First of all, this is the temperature of the reaction vessel, or whatever we're dealing with, and there are 4 columns in terms of the number of degrees centigrade it takes to double the reaction rate. So we've got those numbers at 40 kilojoules per mole as an activation energy, 160 kilojoules per mole, etc., etc. Now, there are 2 trends from this data. Just look where the smallest number is to start with. You can see that this column has the smallest number of degrees to double the reaction rate at every temperature. So the implication is the higher the activation energy, the more sensitive the reaction is to temperature. At a high activation energy like this, changing the temperature by a very small amount increases the reaction rate enormously. The other thing to notice as well is the lower the temperature. So now we're going across horizontally here, comparing to the rows below. The lower the temperature, also the more sensitive. So at any activation energy, we'll just stick at 40. At 0, it only takes 11 centigrade to double the reaction rate. But at 400, it takes 65, and 1000, it takes, and so on and so forth. So 2 things. The higher the activation energy, the more sensitive the reaction is to temperature, and the lower the temperature, the more sensitive the reaction is to temperature. Okay, so this is really a summary of that, and I probably don't need to go through that with you. And again, this follows from what we have just talked about, and I'm sort of hoping that this is very familiar to you, or at least time you look at it again and remember what you've done in the past, it will be very familiar to you. So now we come back to our reaction forms and the effect of these activation energy and temperature sensitivities to each of these types of forms. So first of all, we're going to look at the obvious thing, which is, let's take the parallel reaction. If the activation energies are different for A to B and A to C, clearly the form of the dependence will be different. Sorry, let's say that again. So looking at each of these forms, either parallel, series, or some other version, the form of the dependence on temperature will be related to this form here. But the other difference, of course, is if the activation energy for these two steps is different, then the numbers will be different, and effectively the yields you get for each of these things are different. They're going to determine how much of a desirable or undesirable you get in any situation. I'm going to go through a series of examples on these, but before we do that, let's just eyeball this and think about what you might expect. So these are your concentrations of your 4 species, A, B, C, and D, with time. They're just sketched out. There's nothing magic about this. Now, which pathway, A, B, or C, best describes, or is best describes what we think we've got? Now, so think about what you would expect. A going to B, going to C, going to D. You'd expect A to fall, B to rise and then fall, C to rise and then fall, and then D to rise. That's not what we've got there, so it's not A. If we go to C, we expect the previous type of form, but here we've also got A going directly to D. So in fact, you'd have a constantly rising D right from the beginning. There would be no lag, and then you'd have complicated structure underneath. Instead, route B looks the most likely. A goes to B, and you can see they're rising and falling at the same time, and then A goes to C, and C goes to D, and you can see C and D then also are rising and falling at the same time. So the eyeball look at this in a batch reactor would be probably scheme B. You don't lose logic in this. That type of analysis is very useful as a first stop so that you know where you're going. Okay. What I'm going to do now is just confirm the definitions of the 4 variables that we've been thinking about, or metrics we've been thinking about. X, conversion, Y, yield, Y bar for multiple reactions, and also for instantaneous yield. Okay. Instantaneous, this now is this form. You've got the effectively parallel of A going to D, desired, or A going to U, the undesired. Instantaneous selectivity is obviously going to be that. Overall selectivity here, and then in terms of your stoichiometric coefficients. And note, if you're in a batch reactor, you're dealing with N, the number of molecules or moles. If you're in a flow reactor, you're dealing with F. Good. Okay. This is just a summary. I'm not going to go through this. We've done this already. And again, it's a summary, but we're now going to start thinking a bit more carefully about how you use this. So we've got a situation now where we've got a parallel reaction, something like that. And, no, sorry, not parallel, you've got a serial reaction. In fact, I can't go back and find it for you. Where A goes to D, the desired, and then D goes to U. And with rate constants KD and KU. Now, if KD is much smaller than KU, it's really rather difficult to get D, because effectively this is very slow and then that's very fast, so you don't know which is controlling. So yeah, vice versa, of course, it's much easier. So in those situations, you need to modify your conditions, including excess reagents, to unpick it. Like your instantaneous selectivity, all things being equal, is defined like that. Again, the same as previously, and the instantaneous yield like that. So there's nothing particularly new there. We're sticking with this scenario now and looking at the on the next slide, the definitions of overall selectivity and overall yield. And again, N or F is dependent on the reactor context. So overall selectivity, again defined as previously, either in a batch reactor here or in a flow reactor here. And overall yield, a la. Okay, and N or F depend on your reactor context. Right, just having a quick look at the time. Okay, we've been about 45 minutes. I may have to, oh no, I think it might be quite quick. Okay, again, selectivity and yield. So the $54 million question, how do you increase yield or selectivity? And the last part of this little lecture is going to be about that, and we've got about 5 minutes left max. Selectivity is certainly the key to waste minimization, but you need to think as chemists what you mean by it. You've got chemicoselectivity, competition of different functional groups, diastereoselectivity, one diastereomer against another, enantioselectivity, formation of one pair of enantiomers, regioselectivity, ortho versus para, aromatic, stereoselectivity. You can read them, I don't need to go through that. I'm now going to carry on and look at some of the ways you can tweak these things through. That website, I'm not going to go to it here. Again, it's Vogler Online. There are some problems there which will help you. I will, in the workshop, be using some of these to work through with you, not particularly from there, but either leave and spill or whatever. Both of these are available on the web. In chapter 1, you'll recognize mole balance and you'll recognize conversion and reactor sizing. These websites are useful as well as the textbook. There is a package called Polymath on your phone, and I'll talk to you about this during the verbal lecture. Okay, now what I'm going to do is walk through a couple of extracts and show you exactly the process you need to use and how you tweak stuff. So let's take this as an example. We have A going to an undesired product, and A going to, a desired product and an undesired product. How do you determine how to set up your plant or your reaction conditions to bias it one way or the other in favor of hopefully your desired product? First of all, write the scheme out so you're very clear about what scheme you've got. If you've got the wrong scheme, then unfortunately everything else is going to go horribly wrong. Write out the rate equation for each of the paths. So for formation of the rate formation of R, the desired product, you can write out the rate constant times the concentration of A to the order, dCr over dt, and for the undesired product, the same. So that's the second stage. First stage, write out the scheme. Second stage, write out the rate equations. And the third stage is to divide the desired by the undesired. So you put the desired rate equation on top and the undesired rate equation beneath. Now clearly all we now need to do is we need that ratio to be as large as possible. So now we know what the aim of the exercise is, we know what we're going to be doing. Okay, this is sort of obvious in one sense. We need this to be, our ratio to be as large as possible. Now, the only factor in this rate equation is the concentration of A. These are constants, and the orders are constants as well. So effectively, the reaction which is of the higher order is the one which will be favoured by the concentration level of the reactant. So if A1, and A1 is the order of the favoured reaction, the order of A in respect to the favoured reaction, if A1 is greater than the desired is greater than the undesired, then a high reactant concentration will increase that desired over undesired ratio. Therefore, a batch or flow reactor would favour the formation of product R, and you want minimum reactor size. If, on the other hand, unfortunately, your undesired product has a higher order, then you need low reactant concentrations, which will favour the undesired product less. But then you'd need a large mixed flow reactor. And if they're the same, the order of both is the same, it's going to be, you've got basically a constant ratio. It's going to be unaffected by those sorts of considerations. So, in summary, when you're dealing with reactions in parallel, the higher the order will favour the reaction with that higher order. So, there you go. First tweak that you can do for these type of situations. Okay. This time we haven't got a unimolecular type situation, just A going to B, but the reaction with another reactant B. We follow the same process. Make sure first of all that you know what your reactions are, the desired and the undesired. Write out the rate equations and, as previously, put them one over the other. Now, before we can go any further, we need to think a bit about the reactor side of manipulation. So we're going to come back to this in a moment. Notice the different reaction orders that we've got up here. So hold that thought, we're coming back to it in a moment. Reactors, we'll just do with mixing models because we have, as you'll see in a moment, we can match reactors to these mixing models. When you just add A and B into a reactor together, both A and concentration of A and B are both high. That's one condition that you may or may not want. If you add A and B slowly, but at the same rate, then the concentrations of A and B are both low, but they both stay low. Equally, you can fill up with A and add B slowly, have high A and low B. You can see there are a number of connotations here, ways you could do it. Let's now look at how there are reactor equivalents to these. So if you have a plug flow reactor or a batch reactor, you can have A and B both high in a plug flow, or in a batch reactor, A and B both high just by adding them both. With a plug flow, if you modify the relative flow rates of A and B, you can have A high or low, B high or low. And likewise with batch, if you start by filling up with one reagent and then adding the other one, you can again get the different conditions. Okay, so there, if you like, the reactor equivalents to our adding of beakers as we were just doing there. Now let's go back to our problem. This was, if you divide one rate equation by the other, you end up with that. So this is the ratio we have to manipulate. Now, in this case, this needs to be as large as possible, and according to our rule for reactions, we're going to need to keep A high, the concentration of A high and B low, because A is for the desired. So the type of model you would want to use for this, you either have A going through in a plug flow reactor with B being added at lower rate, or you have you could start with a beaker full of A and put B in slowly. That would be equally good. These are the most desirable, and moving that way shows how your process gets steadily less desirable in terms of how you're trying to tweak this. So your best bet if you're doing a batch reactor is put A in the batch reactor and add B slowly. That way you have A high and you have B low, which means you'll maximize the product you want. So you see this sort of thinking and this sort of modeling is, I wouldn't call it modeling, is exactly the sort of stuff you're going to be doing when you design your processes. Okay, so let's just go through this again, this process. Establish how many products you have, which is desirable, write out the equations and all the scheme, the rate expressions, form a ratio, then decide which you control, and then start thinking reactors. Okay, this has been a reasonably long one, so thank you. I think we are just about finished tonight, and I'll see you later. Take care. Bye-bye.